be commoditized. And finally, open source toolboxes like you see on the right-hand side, TensorFlow, PyTorch, Keras, and so on, make it very, very streamlined and very easy for all of you, just in a 1-week course, to get hands-on with these architectures and start to build directly. So let's start by, just understanding the fundamental building blocks of every neural network, and that's just a single neuron or a perceptron, right? So what is a perceptron? The idea of a perceptron or a single neuron is really simple, right? So let's start by just taking and defining a perceptron purely by its forward propagation of information. So given some inputs, how does a perceptron compute an output? Let's start by defining, a set of inputs, x1 to xm, and each of these numbers, each of these inputs will be multiplied by a corresponding weight, w1 through wm. What we're going to do is, after we do this multiplication, we're going to add up all of those numbers together. We'll take the single number that comes out, and then we'll pass it through what's called a nonlinear activation function. This is just a nonlinear one-dimensional function that you can pass through this single number into the output. Here it's denoted as g. Okay. I left out one minor detail, so I'll correct it right now. So the one thing that we have to remember is that after we multiply all of our weights by our inputs, we're also going to add this one number called a bias term. And the bias term is effectively, if you look at the equation, it's a way for us to shift left and right along our activation function g. So this is just a shifting scalar designed within the equation here. Now, on the right-hand side of this slide, you can actually see the diagram on the left mathematically illustrated or mathematically written as a single equation, right? Now, I'm going to now rewrite this for the sake of cleanliness using linear algebra in terms of vectors and dot products. So let's do that now. So now instead of, x1 through xm, I'm going to write just a vector, capital X. Capital X is going to be a collection of all of my inputs, and capital W will be a collection or a vector of all of my weights. The output then, y, is simply just going to be obtained by having a dot product between x and w, adding our bias, and passing through g, passing through a nonlinearity.
I mean, how does it look like?
Now, you might be wondering, I've mentioned this nonlinearity a few times. What is this thing? Well, I said it's a nonlinear function, right? But what exactly is it? One common example here would be what's called the sigmoid function. So the sigmoid function, you can see right here, it basically can act over any real number on the x-axis, but it outputs only between 0 and 1. So usually the sigmoid function is really good for things like probabilities. If you wanted to convert your output of your perceptron, your neuron, to a probability. But in fact, actually, there's many types of nonlinear functions. It's just one function that's commonly used in neural networks. But throughout this presentation, you'll see basically a few examples of different nonlinear functions. And also, I'll point out on the bottom of this slide, you can see some code snippets, both in TensorFlow and PyTorch, that will help kind of like align what you're seeing in the math with also code that will be relevant for some of your software labs later today. The sigmoid function that you saw earlier, this output's very good for probabilities. You'll also see things like on the right-hand side, this is called the rectified linear unit. This outputs things that are strictly positive. It is piecewise linear, so it is linear before 0 and is linear after 0, but it has a single nonlinearity at x equals 0. Now, why do we need activation functions? Actually, that's a question hopefully everyone here asked. This seems like unnecessary at its first glance. The point of an activation function is actually quite simple. It's to introduce nonlinearities into your model. Right? Without a nonlinear activation function, you have a linear model. So why do we want nonlinearities? Well, it's just because real data in the real world is heavily nonlinear. Right? Now, you might be maybe just a good example to show this would be, let's say I show you this picture here. And if I asked you to build a classifier, a separation, draw a single line that separates the red points from the green points, can you draw that line? At first glance, yes, you could draw the line, but what if I told you that it had to be a straight line? Right? If I told you it's a straight line, then it's not really possible anymore to do this task well.
So in a
So
sense
that makes the problem really hard. That's the problem with having a linear model. The benefit of having nonlinearities is that it allows us to approximate arbitrarily complex functions with enough depth in our model. This is exactly what makes neural networks, nonlinear neural networks, extremely powerful. Let me just help you all understand this with a simple example. So imagine I gave you now a trained neural network that you can see here. It has one perceptron, right? But it has two inputs, x1 and x2. It also has two weights, w1 and w2, and it also has this bias term on the top as well. Now, how would we process this information? It's the same story as before. We're going to compute a dot product. We're going to add the bias and pass it through our nonlinearity.
Contains infinite number of points. And
now, if we plug in our data, we already know our inputs. Here, our inputs are going to be, it's positive 3 is the first input, x1, and negative 2 is our second input,
what we started with,
we can plug these into our equation along with our weights as well. And we can see, actually, that we can obtain this line, which is going to be a two-dimensional line that parameterizes our entire function space of this neuron. Since it's only in 2 dimensions, we can even plot this line. So we can say exactly how this whole space would look like. And for any new input that this model sees, where, with respect to this line, would it fall? So let's say, for example, that if I had this new point, here the point is on this x1, x2 space, it's going to be at point -1 by 2.
Yeah. So
we can see graphically exactly where on this plot it falls with respect to the line. Now, also we can plug it back into our equation as well, and we can see exactly, okay, if we plug in
if there is a model function,
or excuse me, -1 as our input to x1, positive 2 to our input of x2, we can plug it into the equation on the bottom left. We pass it through the nonlinearity. The nonlinearity here is a sigma function, which washes everything to be 0 and 1, depending on which side of the line it falls on. And we get this final answer. Here in this case, the final answer is 0.002. Right? This is less than 0.5. 0.5 is going to be the divider because all of our outputs are going to be separated between 0 and 1. And we can actually graphically represent this as well. So if you fall directly on the line, your output after nonlinearity is going to be 0.5. The more to the blue side that you fall, the farther under 0.5 you are. And the more to the green side you fall, the farther above 0.5 you fall. So the line basically represents the point of separation between these two sides of the space. And depending on which side of your input you fall on, this is the way for you to classify this point as either a positive point or a negative point. So now it's also important to understand, we just did this for a single neuron with 2 inputs. You can imagine that if you had a model with many more inputs than 2, it would no longer be possible to draw this plot. And this is something that we'll have to deal with in terms of understanding and building intuition. But hopefully, even at the small scale, you can build some level of intuition, even with this plot. Let's see how we can now start to tie some of this together to go beyond just one neuron and start to build networks, right? Because this is where we actually build really powerful systems. It's not just from one neuron, but from full networks. So to do that, let's just revisit our diagram one more time. If there's a few things that you take away from this class, this is hopefully the slide that you take away from, right? And I've said it already a few times. I'll say it one more time. How do you pass information through a neuron? You take a dot product, you apply a bias, and you apply a nonlinearity. These are 3 steps, and these keep getting repeated over and over again. I will simplify the diagram since I've now told it to you so many times. Hopefully it's starting to stick now. I'm going to remove all of the weights from this diagram, and I'm also going to remove the bias term. So now you can always assume that those 2 things are there. I'll just remove them from the illustration moving forward to keep things cleaner. Now Z here, Z is going to be the result of that term. It's going to be the result of the dot product plus the bias. It's going to be before the nonlinearity G. Okay, so we will then pass Z through G, and that will give us Y. And you can see that represented right here. Okay, now what if we wanted a multi-output neural network? not one output, but two outputs. How would we change this picture? Okay, actually it's pretty simple. We now just create a second perceptron. We now have two neurons instead of one neuron. Both neurons have the exact same inputs, but because their weights are different, they will have two different outputs. So they both take as input the same information, they process it their own way with their own weights, and they make two different outputs from scratch.
Absolutely continuous.
Now, these types of layers, let me call them a layer, are typically called dense layers because everything in my inputs is connected to everything in my outputs. And if you exclude the nonlinearity, this is also a linear layer.
Distribution function will have
this is a linear layer because it takes all of my inputs x and just linearly operates them with my weights w and adds a bias, which is also a linear operation. So we can now actually implement this entire operation from scratch in Python. So let's try it out. So we're going to start by just defining those two weights. We define self.w, this is our weight vector, and we also have self.b, which is our bias scalar. This is just one number. But here, since it's an entire n-dimensional output, we'll actually have n neurons in the output as well. When we want to do our forward pass through this layer, how do we do this? It's the same story as before. We take a dot product, which here is this matrix multiply. We add the bias, and then we apply our nonlinearity. This is the sigmoid here, but you could change this to any nonlinearity. In PyTorch, you can actually see that there's almost perfect analog on the left and the right side. It's the same story. Here you create your two weights, your weight and your bias. You apply a matrix multiply, add the bias, and apply your nonlinearity. Exactly the same as before. Now, luckily, TensorFlow and PyTorch have already implemented this type of dense or linear layer for us, so we don't need to do that. That was just a good learning exercise, what we just went through. But here you can just call it, right? You can see the function calls on the bottom.
Singular.
Now, let's take a look at a single layered neural network, a single hidden layer. So not where the output is directly from a single perceptron, but where we have to actually pass through two layers. Okay, what does that look like? So this is one where we have the single layer, single hidden layer is placed basically between our output layer and our input layer.
Singular distribution?
Why do we call it hidden? Well, it's just because we don't directly observe the data that happens in this layer, right? Input layer is data that we provide to the model. The output layer is typically things that we would supervise over. The hidden layer is one that is learned over the course of just observable data. Since we now have a transformation both from inputs to hidden and from hidden to output, we now have two layers, right? And that's also going to mean that we need two weight matrices, W. So we'll actually have a W1 on the left-hand side and a W2 on the right-hand side. Now, if we look at a single unit, a single perceptron, a single neuron in that hidden layer, let's take Z2, for example, it's just a perceptron that we saw before. It's the same story. Nothing here has changed. Its answer is computed by taking a dot product, adding a bias, and passing it through this nonlinearity. If we took a different node, a different neuron, let's say like Z3, the one right below it, it would also be computed with a dot product, bias, nonlinearity. It would take the same inputs as Z2,
important properties of the
it would have different weights. So the dot product and the bias would be different. This picture, again, looks a bit messy, so I'm going to simplify it even more. I'm going to replace all of the arrows with the single icon here, the symbol, which is just going to denote this dense layer, this linear connection layer that is happening between these two components.
Distribution
and again,
singular distribution.
We can see that to build a network like this in TensorFlow PyTorch, these convenience functions are really starting to help us a lot because we don't have to implement a lot from scratch. Now, if we wanted to create a deep neural network, how would we do that? What is a deep neural network? It is nothing more than just sequentially stacking more and more of these linear layers, followed by nonlinearities, followed by more linear layers, followed by more nonlinearities over and over and over again in a hierarchical fashion. So this is just a model where the final output is created as a hierarchical combination going deeper and deeper into these linear followed by nonlinear operations.
This is the definition.
Yes, please.
an absolute continuous distribution, we have absolute continuous distribution. Okay, maybe. Yeah, not
exactly. Yes, of course. Question was about maybe just for a quick real-world example of why we would have a different layer, so different layers on the depth axis, but also different outputs on the up-down axis, right? So different layers on the x-axis. Basically, this corresponds to more depth, more complexity in your network, right? So for more complex tasks, you would want more depth because you're introducing more hierarchical nonlinearities. After one layer, if you have a single, dense connection followed by a nonlinearity, you have a limited amount of complexity that you can extract. It's only coming from one nonlinearity. So it's limited to the expressive capacity of that single nonlinearity. So as you get more and more complex tasks, you require deeper and deeper expressive functions. So that's this one axis. On the other axis, more outputs. This is just a problem definition. So if you wanted to predict more things, then you would need more outputs. A good example is that if you wanted to do generation, right? Let's say to generate an image, you would need to generate values for every pixel in that image. That's a lot of outputs, right? Versus if you wanted to just predict, let's say, the weather tomorrow, that's a temperature value, right? It's just one output, just number, right? So depending on your problem definition, those two things can change. Excellent. Okay, so now that we have an idea of architecturally what makes up a neural network, I think now it's time that we can actually start to compose all of this together. And actually in line with that example, that question that just came up, let's try and go through an example of applying some of this theory into practice and actually understand, how we can look to apply a neural network to solve a very real problem. Let's say maybe not that real, but maybe real for all of you that you've been thinking about it. So here's a question that maybe all of you have been asking yourselves: will I pass this class? And let's try and build a neural network that can infer or predict this answer for all of you. So we're going to do this by building a very simple model. It will take as input two inputs. One output. The one output is going to be, will I pass this class? Yes or no. So a single number probability of passing the class. And it will be two inputs defined by number one, how many lectures you attend over the course of this 1 week. And number two, the number of hours that you spend on your final project. Okay, so let's plot. Because we've taught this class for many years, we actually have data from past students on this operation. We can look at all of the green points are people that have passed the class, all of the red points are people that have not. And we can also plot where you are, or you can guess how many hours you're going to spend on this class, how many hours you're going to spend on the final project. And what we want to do is build a neural network that will determine from all of this past data, of all of these past students, where will you fall on this probability chance of passing versus not passing. So let's do it. Okay, we've actually learned all of this so far in the class, so let's take it step by step. We have two inputs. This is this new person, right? You have spent 4 lectures you've attended, and you spent 5 hours on your final project. Those two numbers you can feed in as input on the left-hand side to your model. We also have a single layered neural network, a very basic neural network. We're just going to start with this for now. And we're going to see that our hidden layer has 3 hidden units, and our output will just have one output, which is a binary output, yes or no, on passing the class or not. And what we're going to see is actually that this model got the answer very wrong. It predicted that you would pass the class with